In this unit on integration by substitution, I'd like to do a couple of examples with you to get you started on this sort of problem. As you can see, there's two examples on the screen. The first one, we'll do the one on the left, find an antiderivative of sine x cos x squared. So the first thing we're going to do is write that as an integral, sine x, and I'm going to rewrite cos x squared in that form. And the reason for that is what I want to try and do is highlight some patterns that tend to occur if integration by substitution is going to work for you. And one of those patterns is, more often than not, if there is a function that is inside a set of brackets, so under a square root sign, raised as an exponential function, so something like that, then more often than not, that is going to be our function that we substitute. Okay, and in the videos you saw, you've seen already, or in the classes that you've attended, the traditional way that we do this is we let u be equal to that particular function. All right, so we're going to let u be equal to cos x. Notice it's not cos x squared, it's not, it's just cos x. And then we're going to find, well, we're going to find the derivative. Now, the reason for that is you'll notice that we've got this dx here on the end, but if we substitute out, I'll go to the next step. If we substitute out cos x for u, we end up having u squared. Now, that's not very good because we can't integrate u with respect to x. So what we need to do is we need to replace the derivative with respect to x with the derivative with respect to u. So I'm just going to do that derivative there. So du dx is equal to minus sine x. Now, one of the next topics that we're going on with, that you'll do in specialist maths, is differential equations. And what we'll learn in differential equations is, whilst du dx technically isn't a fraction, we can treat it like one. So we can actually then go, well, if du dx is equal to minus sine x, then du is minus sine x times dx. Okay? Now, well, once we've got that particular function, then I can make, well, I don't want dx over here, okay? I don't want this dx here, right? What I want is du. So I'm going to rewrite my function by substituting out the dx as well. So now I'm going to have minus 1 on sine x, okay? I've just taken the minus sine x to the other side of the equation, multiplied by du. So now, so this is a little bit of working out done over here. So now my integral is equal to sine x multiplied by u squared multiplied by, and I'm going to replace dx with what I've just discovered dx is equal to. Now, what I will hope you will find, now if integration by substitution is going to work, then you should discover that this function will cancel out this function. Okay, if it doesn't, then integration by substitution, there's two things that will happen. Either integration by substitution isn't the correct method, or you've made an error. So always check to make an error, see if you've made an error first, and then try a different method if this one doesn't work. I haven't made an error, and it does cancel out. So we're on the right track here. And so we're left with the integral of u squared, and there's a negative sign there. So I'm just going to take it out the front because it's like -1, so I can take constants out the front, times du. Okay, so that's going to equal to negative u cubed on 3 du. No, du is gone, my apologies. So we're taking the integral plus, I won't put a plus c in yet. And that's equal to, well, we know what u is. U is negative cos x cubed plus c. And you can write that, if you want to, as negative cos cubed x plus c, but there's no requirement that you do so. Okay, so that's our first example. All right, so let's have a look at the second example over here. So the next one is find the derivative of that. So what I'd like you to do in this case, give you a couple of seconds, jot that question down on your paper. All right, and then underneath that, then write down the function that we're actually integrating. So we're going to integral of 5x squared multiplied by x cubed minus 1 to the power of a half dx. And then over here on the right hand side, where you've got a little bit of space, I'd like you to write down what function do you believe u is going to equal. Well, I'm hoping that you will know that u, wherever possible, is the function inside the brackets in this case. So in this case, u is going to be x cubed minus 1. So then we're going to go du dx is equal to 3x squared. Therefore, du is equal to 3x squared dx. So dx is equal to 1 on 3x squared times du. Pretty common patterns are going to happen here. You'll notice that we've got a fraction for in our dx, as we did over the other example. That's because we want to actually get rid of the 5x squared. So by having a fraction, that's going to help us do that. Technically, we want to get rid of the x squared part, more specifically. So I'll just write down what we've got. So we've got 5x squared multiplied by u to the power of a half multiplied by, so dx is equal to 1 on 3x squared times du. So what we see now is the x squareds cancel, which is what we want to happen. We're left with 5 over 3, so we'll take it out the front because it's a constant. Integral u to the half times du. Okay, and then we've got 5 over 3, integral of u to the half is u to the 3 over 2, divided by 3 over 2, add 1 to the power, divide by the new power. Okay, so let's just rearrange that. So 5 over 3, whoa, sorry about that, bumped the screen. So 5 over 3 is going to be, so that's going to be 10 over 9 times, now u is equal to, what did we say it was, x cubed minus 1 to the power of 3 over 2. We can leave it in that form because our question was given the power of a half, so we can just leave it like that, plus c. And there's our solution. Now, there is another example in your textbook, so the Cambridge textbook on page 397, which is worth having a look at. And also on page 398, you might want to go to your online textbook for these ones because they're slightly more complicated, but there is the video of the worked solutions for those. And they're worth having a look at because not only do you have to do integration by substitution, but you also have to then apply the integrals of the inverse functions that we did in a previous lesson. So have a good look at those. They'll be really good examples of complex familiar problems that you could experience on your end of Unit 4 exam in future reference, or for 2020 on your external exam. All right, and then there are some questions to have a go at in exercise 11D. Good luck.